Imagine a Parquet file containing 1 million rows. Now imagine that you need to just delete one row. Parquet files are not designed to edit individual rows in place. So traditionally, the processing engine has to read the affected file, remove that one row, write a completely new Parquet file, and update the table metadata to use the new file. That's a lot of work to remove one new record. But Databricks can avoid that immediate file rewrite using a feature called deletion vectors. Deletion vectors allow delete, update, and merge operations to mark individual rows as modified without immediately rewriting the complete Parquet file containing those rows. So in this video, we will answer 5 questions. What exactly is the deletion vector? How does a delete work with it? How do update and merge use it? How do queries still return the correct data? And when is the deleted data actually removed from the storage? By the end, you will understand the full life cycle from logical deletion to physical file cleanup. Hello everyone, welcome to BigData Factor. I am Pranit and I have 4+ years of experience working as a data engineer. If this is your first time visiting this channel, don't forget to subscribe for more content on big data and real world insights. Here is the flow for this video. We will go through why row level changes are expensive, what a deletion vector stores, delete, update and merge behavior, how reads return the correct result, and physical cleanup and limitations. Let's begin with the core problem. Why modifying Parquet is expensive. Suppose one Parquet file contains rows like 1, 2, 3 to up to 1 million. Now what happens if we run delete on this Parquet file for a particular row ID? Assume the matching row is stored inside that file. Without deletion vectors, Databricks cannot simply open the Parquet file, erase that row, and save the same file. The normal approach is read the affected file, remove the matching row, write a replacement file, and remove the old file from the current table snapshot. Even though only one row changed, the full affected file may need to be rewritten. This is called write amplification. A small logical change creates a much larger physical write. And this becomes expensive when a table receives frequent delete operations, update operations, and merge operations. And Databricks documentation describes the exact problem. Without deletion vectors, changing a small row requires rewriting the entire Parquet file containing that one row. So the question becomes, can we record that a row is no longer valid without rewriting the base file immediately? That is the purpose of a deletion vector. Now the next part, what is the deletion vector? A deletion vector is metadata that identifies which rows inside the file should no longer be written as part of the current table state. Imagine this Parquet file. Now imagine that order 1001 is deleted. Instead of rewriting file A immediately, Databricks can return the file and record something conceptually like this. Here, the Parquet file still physically contains the row, but the delta table metadata now says, when reading this file, do not return the row at that position. Databricks describes deletion vectors as metadata-based soft deletes. The row modification is recorded separately, and readers apply the deletion vector entries when resolving the current table state. The important word here is logical. The row is logically removed from the current table result. It may still physically exist under the original Parquet file until a later maintenance operation rewrites that file. Let's pause for a second. So far, we understand why one row changes can be expensive. We understand that a deletion vector marks row positions. Now we need to see how table operations use it. The next question is, what happens when we run delete, update, or merge? Consider this delete statement. Without deletion vectors, it will find the affected file and rewrite that file without order 1001. And with deletion vectors, it will find the affected row, record the row as deleted, commit new table metadata. The original Parquet file does not need to be rewritten immediately. The table gets a new delta version, and queries against that new version no longer return the deleted row. That is why point deletes and small selected deletes can become much more efficient. The benefit is larger when the number of changed rows is small relative to the size of the files containing them. Now consider an update query. An update changes an existing row. Conceptually, Databricks can treat this as two actions, marking an old row as no longer current, updating a new row as new data. The old row can be represented as modified through the deletion vector instead of forcing an immediate rewrite of the full original Parquet file. The updated row is then stored as part of the new table data. So the current table snapshot returns the new version of the row, not the old one. Now consider merge. A merge can contain several types of changes: update, delete, or insert. Deletion vectors can help Databricks avoid immediately rewriting complete target files for matched rows that are updated or deleted. New or updated row data is written separately while the old matching rows are logically removed. Databricks supports deletion vector acceleration for delete, update, and merge. Support details depend on the runtime, photon usage, and client version. But deletion vectors do not mean that every merge automatically becomes fast. Databricks still needs to find the matching target rows. A poorly written merge condition may scan the large part of the table. Here, deletion vectors optimize how affected rows are modified. They do not remove the need for good data layout, selective predicates, appropriate clustering, file pruning, and efficient join conditions. The next part is how reads return the correct data. At this point, the base Parquet file may still contain logically deleted rows. So how does a normal query avoid returning them? Suppose a query reads, Databricks resolves the current table snapshot using the transaction log. The snapshot identifies the active data files, the deletion vectors associated with those files, and the current version of the table. Here, the read path is conceptually read active Parquet file, read associated deletion vector information, and exclude logically deleted row positions, and then return the current table result. So the user does not need to manually filter deleted rows. Normal table reads apply the deletion vector information automatically when resolving the current state. This is similar to putting a transparent filter over the base file. The physical file says that rows exist. The deletion vector says those specific positions should no longer be visible. Together, they produce the correct logical table. So here the performance trade-off is deletion vectors reduce immediate write amplification, but they are not completely free. Reads may need to apply traditional metadata to determine which rows should be skipped. If a table accumulates many modifications without file maintenance, read behavior and file layout still need to be monitored. This leads to the next important question. What are the changes physically applied to the Parquet files? A deletion vectors creates a soft delete. That means the row is hidden from the current table, but may still exist physically in the base file. This distinction matters for storage cleanup, time travel, compliance requirements, and permanent data erasure. To physically apply the changes, Databricks must eventually rewrite files that contain soft deleted rows. Databricks documents several operations that may apply deletion vector changes to physical files, including optimize, auto-compaction, and rearg table apply purge. The rearg apply command specifically rewrite files containing soft deleted data. The most explicit purge command is rearg table name apply purge. Conceptually, we have old file plus deletion vector. We rewrite only active rows and then create a new clean file. After that rewrite, the logically deleted row is no longer present in the current table's active files. However, the older file may still be retained for table history and time travel. To physically remove expired old files from storage, we use vacuum. The complete cleanup process is deletion vector creates soft delete, rearg table apply purge rewrites current files, and at the end, vacuum removes expired old files. Databricks notes that after rearg table apply purge, the old data may still be available inside older files referenced by historical table versions. Those old files become eligible for physically deletion only after the configured vacuum retention period has expired. This means reorg applies the deletion to current files. Vacuum removes expired historical files. So do not reduce the vacuum retention period casually. A shorter retention period reduces your available time travel and recovery window. And if older clients or long-running jobs still reference those files, aggressive cleanup can create problems. So the next part is how to enable deletion vectors and compatibility. For delta lake tables on Databricks deletion vectors can be enabled using a table property or during table creation. Current Databricks documentation says that deletion vectors must be explicitly enabled for delta lake tables, although workspace defaults can automatically enable them for newly created tables in supported configurations. and Apache Iceberg v3 tables on Databricks include deletion vectors by default. But there is an important compatibility warning. Enabling deletion vectors upgrades the Delta table protocol. That means clients that do not support deletion vectors may no longer be able to read the table. Before enabling this feature, check Databricks runtime version, external data clients, Delta sharing consumers, and other engines reading the table. Databricks currently recommends runtime 14.3 LTS or later for writing deletion vectors tables with all available optimizations, while supported reads begin with earlier runtimes. Exact support varies by operation and client. Deletion vectors also support another important Databricks compatibility, row-level concurrency. Without row-level concurrency, two writers modifying different rows inside the same physical file may still conflict because both operations affect the same file. With supported row-level concurrency, Databricks can detect changes at row level, allowing more concurrent operations that modify different rows in the same file. For current supported configurations, deletion vectors are one of the requirements for low-level concurrency on unpartitioned tables. Exact runtime and table requirements should be checked before relying on this behavior. But deletion vectors do not mean write conflicts are possible. Two operations can still conflict when they modify the same row, when they perform incompatible metadata changes, or when they use unsupported predicates, or when they violate other isolation and concurrency rules. So finally, how does Databricks delete rows without rewriting Parquet files immediately? Here is the complete answer. A deletion vector records which row positions inside a data file should be treated as deleted or modified. The underlying Parquet file can remain unchanged during the initial delete, update, or merge. When the table is read, Databricks combines the active Parquet files with the deletion vector metadata and excludes the logically deleted rows. This reduces immediate file rewriting and can improve the performance of selective row-level changes. The deleted data is physically removed later. Reorg table apply rewrites files containing soft deleted data. Then after the retention period, vacuum can remove expired historical files. So remember this flow: row modification, deletion vector, correct logical reads, and reorg applies the change physically, and finally vacuum removes expired files. So deletion vectors improves the way Databricks handles row-level modifications, but they do not replace good table design, selective merge conditions, file maintenance, compatibility planning, or proper retention management. So this is the complete technical picture. Comment Delta if you want the next deep dive on the Delta transaction log and how table versions are created. If this video helped, drop a like and subscribe to Big Data Factory. This is all for today. We will meet in the next video. Till then, keep learning and keep building. Bye bye.